In video number 297, I started to build a retro computer with parts that were used in the late 1970s. In the last video, we mainly looked at the hardware. Today, we will finish the hardware and start to program the board in assembler, as we did back then. Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. In today's video, we will build the single board computer designed in video number 297. We will test it and I will show you the two most important debugging tools we used back then. Then we will look at how computers were programmed in the 1970s and 80s. For that, we have to repeat the binary and hexadecimal numbering scheme. We will look into the CPU architecture to learn about registers. We will see how detailed assembler programming is and what spaghetti code is. We will see how stacks work. We will have a look at the nice 8085 simulator. Like that, you can program without building the hardware. And we will build a sophisticated Blink program. If you did not watch video number 297, it might be a good idea to do it now. You find a link in the upper right corner of your screen. In the meantime, I included all the enhancements proposed by my viewers and created a PCB. And here is the assembled single board computer a la 1979. Of course, all in through-hole technology. I have to admit, I like how it looks. Let's do a quick walkthrough and start with these two big chips. This one is the 8085 CPU and this one is the 8155 I/O and memory chip. The 8155 offers 3 8-bit I/O ports, a timer and 256 byte of RAM. The CPU and the I/O chips are connected by an 8-bit bus that carries addresses and data in a multiplexed manner. If we go by size, we continue with the 2732 4KB EEPROM and the HM6116 2KB RAM. Unfortunately, they do not understand multiplexed buses. This is why we have to demultiplex the addresses from the data, which is done by the 74LS373. The 74LS373 is a better choice than the 74LS273 used in the last video. I could have also used a 74LS573 for the same purpose, but the PCB layout was easier with this one. The LS373 has 8 input lines for the multiplexed signal. It uses the ALE signal supplied by the CPU to store the address part of the signal. So, at the 8 output lines, we have a pure address bus. Together with the other address lines provided by the CPU, we have 16 address lines, which can address 64 kilobyte. The EEPROM, as the chip with the biggest capacity, uses address lines from A0 up to A11. And the smaller RAM chip only up to A10. The 8155 only uses A0 to A7. Without care, they would use the same addresses and the CPU could not distinguish between them. We have to assign different parts of the 64K address space to each chip. That is why we feed A12, A13 and A14 into an 74LS138. Its truth table shows that if all 3 address lines are low, Y0 is also low. If A12 is high, Y1 is high. And if A13 is high and A12 low, Y2 is low. Very good. The CPU expects its first instruction at the address 000 hex. This means all address lines have to be low. If we connect Y0 to the chip enable, the EEPROM will answer if 0000H is called. Exactly as needed, because there the first instruction will be stored. If we connect Y1 to the chip enable of the RAM, it will answer if the CPU asks for address. Not easy for guys who only calculate in decimal numbers. Maybe easier for the Americans, because they are used to weird numbering schemes. They can add 5 feet and 3 inches directly in their head, for example. Unbelievable for a Swiss. Anyway, I deviate. If you want to step back in time, you have to learn the binary and the hexadecimal numbering. No way around it. In our case, it is easy. We have 16 address lines from A0 to A15. So the binary numbers are 16 characters long. For example, the first address for the EEPROM is 0000 0000 0000 0000 binary. And the RAM chip starts on 0001 and the rest all zeros, also in binary, because the chip is only enabled or selected if A12 is high. The binary system is not very convenient to use, because we have to write a lot. This is why we usually use hexadecimal numbering. 4 bits are put together and form a number from 0 to F, F being 15. So the start address of the RAM chip is 1000 hexadecimal now. You can calculate the start address of the I/O chip yourself, just to test if you understood the principle. The board also contains a CD4040 counter chip, which is not used today. It can feed the timer and create interrupts. And we have to discuss one other specialty of the 8155 chip. As said before, it has 3 ports and a timer, which are, similarly as with the Arduinos, controlled by registers. Register 0 is the control and status register. And the other 3 registers are used to read from or write to the pins. Enough hardware. Let us do the software now. Computers are controlled by instructions, not commands as we use in modern languages like C++ used by Arduino. These instructions are much more primitive. To understand these instructions, we have to zoom in to the architecture of the CPU. We find it on the first page of the datasheet. We will not cover the whole architecture and focus only on the different registers, as storage locations inside the CPU are called. Because the 8085, like the Atmel 328, is an 8-bit CPU, most registers are 8-bit wide. Let's start with the most prominent one, the register A. It is most versatile. For example, you can add or subtract the content of another register from register A, or you can compare the content of register A with a fixed number. These calculations are done by the arithmetic logical unit, short ALU. The next special register is the program counter. It always points to the address of the current instruction. And because the 8085 has 16 address bits, it also is 16 bits wide. The program counter usually starts at address 0 hex and counts up. We will later see that this is not always the case, fortunately. The next category is general purpose registers called B, C, D, E, H and L. They are all 8 bits wide and sometimes can be combined to 16 bits. The last one is called stack pointer. It is 16 bits wide, and we will see that it is the base for an extremely important concept in computing, last in, first out, or LIFO. Now we only need a list with all instructions available for the 8085, and we can start to code. We can do it on a sheet of paper, as we sometimes did back then. To test our computer, we could create a simple program which loops. Nothing more, but also nothing less. As said before, after reset, the CPU looks at address 0 hex for its first instruction. If it would find, for example, 0 hex, it would not do a lot, because this is the opcode for NOP or no operation. The only thing it would do is to increase the program counter. Then it would read the instruction at 01 hexadecimal. If we want a loop, we have to find an instruction which jumps back to 0 hex. And really, we find one. It is called GMP, jump. As before with NOP, we do not enter the letters JMP into the EEPROM. We only enter the opcode C3. Of course, we also have to provide the CPU with the information on where we expect it to jump to. This is, of course, a 16-bit address. In our case, we want it to jump back to 0 hex. So our program looks like this: 00, C3, 00, 00, all hex, of course. Simple. If we program this code into the EEPROM, the CPU should start to loop after reset. We can do this with this EEPROM programmer. As seen in the last video, this code will stay there for a long time. You will later see why the programmer, as well as my board, has such a socket. We insert an EEPROM, select the right type, and check if it's empty. Now we can key in our program and hit this P button. Then the program is ready to rumble. We insert it into its place on our computer board and power our newly built computer up. Will it work? At least it has no short circuits and consumes 130 mA. Quite a lot compared with an Arduino. It would be even more if I would use the original parts and not the CMOS versions. But how can we see if the program and the board itself works? Did you see somewhere a serial print? Or even a serial connection? No, of course not. Those things were considered to be luxury at the time. The only tool which can help us is the oscilloscope. The first test is always, does the thing create a clock? Pin 1 of the CPU should oscillate with a frequency of 3.57 MHz as the quartz says. And really, it works. Not a square wave, but it's okay for now. How can we determine if everything works as planned? Now we need the second very important debugging tool of those days. The thing between the ears. Usually it is called the brain. So what would we expect? For example, we would expect that when the program counter counts up, the address bus will show address 0 up to 03 hexadecimal. It should never reach 4 hex. So the maximum address in binary is 11 binary, which means A0 and A1 should move up and down, and all other address lines should stay low. We can probe A0 and see if it toggles. Yes, it changes between low and high, and A1 too. A2 to A7 all stay low, so our program works. If the program would not work, we could start to debug and probe, for example, if the EEPROM is selected. This can be done by probing its CE pin. Here, of course, it is always selected. I have to admit, this program is not sexy. A looping NOP. But we were able to prove that our board works, at least partially. You know what follows. Of course, the blink sketch. By the way, this was not standard procedure back then, because LEDs were too expensive. But creating a blink sketch will take us the rest of the day if we continue like that. Think of what we want to do, search for the right instruction, write it down on paper, key it into the programmer and program the EEPROM. As said before, the EEPROM keeps its content and only can be erased by UV light. This takes about 10 to 20 minutes and is done by this device. More than enough time for you to like the video or to subscribe to the channel if you like the style or the topic. Fortunately, we are 40 years later and EEPROMs are no more so expensive. This is why I bought a few of them and regularly erase them during my other work. so we can continue while our first trial EEPROM is erased by UV light. Already back then, we knew that the productivity of programming had to be increased. This is where programs called assembler or cross-assembler were developed. The main function is to look up the opcodes and the instructions and calculate addresses for jumps. By the way, assemblers work on the same machine as the assembled program, and cross-assemblers run on a different machine. Fortunately, I found a modern cross-compiler for the 8085 and other processors written by San Bergmans. It takes a simple text file and creates an Intel hex file, which can be read by the EEPROM programmer. What an improvement compared to the early days where ticker tapes or even worse, cassette tapes were used. Now we can write our code from before again. This time in a text file called test1.asm. First, we have to instruct the assembler that we will write in 8085 assembler. That we want to start our program at the address 0 hex and that we want to have an Intel hex file as an output. After saving the file, we start the assembler and get this output. No errors. And, as expected, it contains the same code as we produced by hand. We also get a hex file, and if we load it, we see that it fills the EEPROM with the same content as before. We do not need to program it again. So we are ready for the blink sketch. We want to connect an LED to pin PA0 of the 8155. I already included a pin header for all ports and bought a nice little 8-bit LED display. Just be aware, because this LED display is connected to VCC, the LEDs are on if the pin is low. How can we make this LED blink? The datasheet says that we have to set this bit to high in the status register to enable port A as an output. The register has the address 0 hex and one binary or one hex has to be put into the register. The 8085 and the 8155 share a nice concept, the IO/M pin. If high, the registers are selected and, if low, the memory. If we want to write to the registers, we have to use the opcode out 0 hex for the status register, for example. Let us now write the blink sketch. It has the same structure as in Arduino. First, we have to set the pin mode to output. As seen before, this is done by setting register 0 hex to 01. Because we only can output the content of A to a register, we first have to fill A with 01 hex. Then we output it to port 0 hex. Next, we have to write the loop statements. We start with setting PA0 to high. This is done by writing 01 hex to register 01 hex. We use the same procedure as before, and we label the first address with loop. Then we have to delay a little. Unfortunately, we do not have a delay function, so we add a few knobs. Because knob also needs time, I hope it will be sufficient. Next, we set the pin to low and delay using the same methods as before. As the last statement, we have to jump back to the beginning of the loop. Easy because we have a label. Ready is the blink sketch. Let's compile the program the EEPROM and run it. Unfortunately, the LED does not blink. Let's check with the oscilloscope. The program does not work. If we check the address pins, we see that the program loops where it should. Only lines till A4 are active. Where is the problem? Let's check the datasheet. The registers are okay. We write 01 hex to register 0 hex, and we toggle the pin in register 01 hex. And we use the command out. Let's check further. Here we see which pins have to be active. IO/memory has to be 1. Write has to be 0. And chip enable active, which also means 0. Let's check IO/M. It moves. Good. And the right pin? Also good. And chip enable? It always stays high. Not good. Why is that? Do you see it? If I had used the second debugging tool, I mean the one between the ears, I could have seen it already before, when I explained the LS138. The chip enable or chip select signal is either low for the EEPROM, the RAM, or the 8155. Never for two chips at the same time. And I explained that there is a good reason for that. So my concept seems to be completely wrong. The out command has only an 8-bit address, so the top addresses are always 0. Strange. My old Morse trainer was wired similarly, and all drawings I saw are also wired like that. Let's have a cup of coffee and answer some comments from my viewers on YouTube. This is always encouraging. After a lot of Googling, I did not find a solution. There is no more a lot of stuff around from this time, and my old book does not cover hardware. Finally, I found a hint. Do you know where? I read this old EEPROM and searched for the D3 command. And there, the port numbers were not 00 hex or 01 hex, they were 20 or 21 hex. The solution is simple. The out instruction places the left 4 bits to address lines A12 to A15. If I change the out 0 hex to out 20 hex, etc., the LED lights up. The chip enable of the 8155 also moves as expected. Unfortunately, the LED still does not blink. But at least we were able to move the pin. If we look at the signal of the LED, we see that our blink works. But way too fast. More than 20 kHz. You see, these old CPUs were not slow, because they had no overhead. So we have to add many more knobs. Because we have a big EEPROM, we could add 1000 knobs in both places. But this would be stupid. We have to have a better solution. We loop 1000 times. But how is this done? Did you see an opcode for while? Now it starts to get hairy. Or, as we then said, spaghetti. To build such a while loop, we set register A to 0 and then increment it with the command INR A, or increase register A. Then we place our knob and compare register A with the highest 8-bit number we have, FFH, which is 255 decimal. Unfortunately, we can not loop 1000 times like that. 8-bit processors know only numbers till 255. But at least something. To close the loop, we jump to wait 1. But how can we exit the loop? We have to insert a conditional jump to off. It only jumps if register A is FFH. We enter the same wait procedure after we switched the LED off. As the last step, we jump back to loop as before. And because we have to have unique labels, we have to use wait 1 and wait 2. If we now follow the program flow, we see that some spaghettis appeared. The LED still does not blink, but at least the frequency is now down to 109 Hz. So we need a delay which is 100 times longer. How is this done? I insert the code copied from here. When it was a little spaghetti before, now we have spaghetti everywhere. This is why this sort of code was called spaghetti code. Like spaghetti on your plate. Not easy to read. And this is only a simple blink sketch. You can now imagine how this looks if you want to do a real project. Maybe you start now to understand why we were happy when higher languages like PLM also appeared for our small CPUs. These languages were able to deal with numbers above 255, were able to multiply or to divide, and even had floating point arithmetic. Yes, these CPUs are not able to multiply or divide. you had to write the whole code yourself. I wonder if the commenters from video number 240 who wanted to go back to assembler really know what this would mean. To clean this mess at least a little, we can put the delay in a subroutine. This is where the stack pointer comes into play. We have to initialize it at the end of the planned stack. Because we have 256 bytes of memory in the 8155, we could place it there, or at the end of the RAM. Because the stack is last in, first out, it grows from the top, like a beehive. This principle is ideal for building subroutines. As with Arduino, we shift one of the delay instructions to the end of our code and label it delay. Then we place a call delay instruction everywhere we want a delay. What happens if call delay is executed? The CPU pushes or stores the current program counter to the stack and jumps to the label delay. Then it executes the delay instructions as before. In the end, we have to add a ret or return instruction. This instruction simply stores the last address pushed to the stack back into the program counter. Like that, the CPU continues one step after the call statement, as expected. But we created another problem. Do you see it? In our subroutine, we use register B, C, and D. If our code had used one of those registers before the call, it would have lost the content of all those registers. Not good. What can we do? We could, for example, store the registers somewhere in memory before we call the subroutine. Not good, because then the calling program would need to know which registers the subroutine will use. So the subroutine should save all the used registers before it starts and restores them before the return command? Much better. Instead of storing the registers to a fixed location, we push them onto the stack, one after the other. And at the end of the subroutine, we pop them into the inverse order, which means we restore them. Here, the sequence, of course, is important. Otherwise, you search for hours because such errors are really hard to find. Maybe you remember? Today, all this pushing and popping is done by compilers. Also a big relief for busy programmers. Now we have to look at the last concept. How do conditional jumps, for example, work? There is another register called flag or the program status word, short PSW. The 8085 only uses 5 flags in an 8-bit register. The most important two are the 0 flag and the carry flag. The 0 flag is set if a particular register becomes 0. It can be used for conditional jumps, for example. The carry flag is important for calculations. If you add two 8-bit numbers, it is easily possible that the result is bigger than 255. Then the carry flag is set. And it can be used by the next commands, very similar to how we learned to calculate back in the day. When a number was above 9, we had to keep the carry in our head. You see, this can become quite complex. This is why I use these sockets. They allow a rapid change of EEPROMs if another error is detected. And this happens a lot. But there is a better way, especially for beginners. Go to an online simulator to test out your program, or at least some parts, before you put it in the EEPROM. Here I have a rather complex program that creates an LED pattern. It reads 21 different bytes and displays their bit pattern on the LEDs. Today we would call these 21 bytes an array, by the way. It is nice to look at, but not easy to understand. This is why I simulate it first. And I can show you some of the content we discussed before. For example, we see here that when we call delay, the program counter after the delay command is pushed to the stack. Then the two registers B and C are also pushed to the stack using one push command. And finally, the PSW is also pushed to the stack. Then the delay subroutine does its thing. Just to note that if registers A and B are ORed and the result is 0, the 0 flag is set, and the jump, if not 0, is not executed. Here, because the D register is 1, the 0 flag is not set, and the jump when not 0 is executed. I leave you a link to the different programs in the description. Like that, you can try it out yourself. And you also find a link to the Gerber files of the PCB if you want to create your own retro computer. Summarized, we built a nice single-board computer with parts used in the late 1970s. We were able to test it with the two most important tools, the brain and an oscilloscope. Of course, today we could use a logic analyzer. Back then, we did not have such tools, so I did not use it today. For that, we have to learn the binary and hexadecimal numbering scheme. We learned how to program in assembler language and how to burn EEPROMs for testing the software. We saw how complicated even small programs like the Blink sketch were back then. We learned what spaghetti code is and how much nicer structured programs look these days. We learned the important stack or LIFO principle. We were able to see how conditional jumps are executed. We found a nice online simulator for our tests. There we can test our concepts without an oscilloscope, but with our brain switched on. And finally, we were able to program 8 nicely flashing LEDs. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You find the links in the description. Thank you. Bye.